So, good afternoon, everyone. So, as you already received the link about today's session, and today's session topic is EV charging infrastructure. So, today, like the trainer name is Akash Singh Chia, he's the official trainer for like ISA India, and he's having like total 3 years of experience like in this EV industry, and we have delivered so many sessions since last 1 or 2 years. And so today we will give the slides. It's about like the EV charging infrastructure and how the system will go. We will start the topic. We will explain the slides. And if anyone having any doubt, you can raise your hand and you can put your message in chat box, and he will clear your doubt. So Akash, over to you. You can start the session and ask your friends, everyone, to join the meet. Okay, you can share the meeting link so anyone can join this. And by end of this webinar, we'll share the attendance link. So you have to fill it properly, your names and spelling, everything. So we'll share the certificate. We'll prepare the certificate according to that name. And I'll ask everyone. I'll request everyone to post those certificate on LinkedIn and tag ISA India. So you will also get the visibility. Okay. So thank you, Akash. You can start.
Okay. Thank you so much, Raju sir. Just give me a second.
Recording in progress.
All right. Okay, good evening, everyone, and welcome to this technical session on EV, smart EV charging infrastructure. So today we are not going to look at a charger as an isolated box which is installed beside a parking space. So today we are going to understand the complete system behind a charger, where the electrical energy comes from and how it is converted and controlled, and how the vehicles and the charger communicates, and how the user is authenticated and built. Okay. And how multiple chargers can interact with solar energy or battery storage or like the utility grid, and intelligent energy management system as well. So this topic is important because the success of this electrical mobility is depends not only the better vehicles but also on the charging, that is like safe, reliable, convenient, interoperable and economical. So like a high power charger may look impressive, but it is useful only when the vehicle can accept the power and the sites that can supply it. So here the connector and communication standards are also compatible, and the complete system remains within the battery, cable, thermal and the grid limits. Okay, so during the session we will begin with basic energy and power concepts. Then we will compare AC and DC charging. Okay, and after that study uh, we will study about this or the families and the communication standards such as ISOs, and we will then open the charging stations and the vehicle conceptually to understand their hardware and software architecture. And finally we will move uh, into the smart charging, AI based optimization, solar, and battery storage integration and vehicle to grid operation. Okay, and I will regularly give you practical situation and ask you to predict what the system should do. Okay, please participate, because this charging engineering is like best understood by thinking in terms of constraints, decision and sequencing, rather than memorizing connectors names. Okay, so by the end you should be able to trace charging sessions from the grid all the way to the battery, and you can be able to explain what happens when the system needs to reduce the power, or stop safely, or even sends power back towards a building or the grid. Okay, so these are the basic learning objectives, and you will be able to explain all those things, and you will be able to understand all these things. Okay, now let's move forward. The first just give me a second, guys. Okay, so the what our first slide shows, what is EV charging infrastructure. Okay, so we know that charging is becoming like an integrated mobility and energy system rather than a simple electrical socket, right? Or if we talk about a conventional charger which only transfers energy, whereas this smart charging system major communicates, or protects, authenticates, and responds to the vehicle or the user. Okay, so as you can see here, if we talk about this EV charging system, the power we get from the first, we are getting it from the grid. Okay, if I talk about in the modern, in the modern areas, okay, like the energy may start at the utility grid and pass through a transformer and distributed panel, and then it enters into the EVSC charging station through travel through what cable and connector, and finally reaches to the EV battery pack. Okay, so a charging site also needs earthing or protective devices, metering communication, payment or authentications, or just payment and authentication, safety and emergency arrangements, parking and civil infrastructure as well. Okay, so a charger can be electrically functional and still be an unsafe or unusable installation if any of these supporting systems are uh, supporting elements are missing. Okay, so this EVSC charging station electric vehicle supply equipment, elec- electric vehicle supply equipment includes the equipment that safely supplies energy to the vehicle and manages connection, controls and protection as well. So if I talk about the AC charging, the EVSC does not normally perform the main AC to DC conversion. The onboard charger here does that thing, and the station includes the power conversion stage. Okay, and if I talk about earthing and some residual current protection, which are basically central to electrical short, for the shock protection, or some DC leakage detection is especially important because certain DC residual currents can affect conventional AC residual current devices. Okay, and if I talk about metering, so metering can serve operational monitoring, billing, and regulatory purposes. So the meter, the required meter class, and I would say that the treatment depend on the business model as well. Okay, and the communication may be local, such as control plot pilot signals, or networks such as cellular or Ethernet connectivity to the CSMS. So then the civil design, if we say that the parking and the civil infrastructure, so civil design includes the parking geometry, accessibility, and something like the impact protection, drainage, lighting. All these things comes inside this parking and this civil infrastructure. Okay, so this is the basic fundamental. This is how the power flows from the grid directly to the, not directly, and passing through all these energy path. So then after this, your vehicle gets charged. Okay, So once we like see the complete physical chain, so the next step is that to identify all the organization and the system that just exchange energy, data and money around it. So as you can see here, there is just a model is shown here, and you can see here where the users, the systems, or this and around this system, uh, the vehicle infrastructure. You can see here the charging manufacturer, utilities, charging operators. Okay, so if I talk about one by one the utility part. Okay, so basically this utility is responsible for the electrical connection and grid constraints. Okay, then this all these things like the CPU operates physical charges. Okay, and e-mobility service also provider is also owns the customer relationship and app. And if I talk about a OEM levels, okay, so all these things comes inside this charging ecosystems. Okay, and how basically the energy is flowing through the cables and the power electronics, then this the data flows through the vehicle communication, then the charger, then the networks and the backend interfaces. Or if I talk about money and settlement, so in this basically the service provider, utility and the possible roaming partners also work in this. And it's like it basically it is like a it needs all these system inside our charging grid ecosystem. Okay, so this is just the circular path in which the EV ecosystem works. Okay, now let's move forward. Okay, so the main purpose is this slide is just is to list the operational architecture which are connecting user application like CSMS. Okay, this is the CSMS, CPO, utility. All these working systems are connected with the one hour the EV supply, EVSE system. Okay, so as you can see at the center, it is we have our EV battery and the IVSC. On the left, you can see here the charging network operator and the charging station management, um, or supervised sessions as well. Okay, so or at the bottom, if you can see here, is it is the utility provider grid connection. Okay, so this basically while an aggregator can combine many flexible loads or vehicle for demand response or some market participation as well. So if you see at the customer support, so customer application or driver fleet, if we talk about this, so in this the main the preference I would say are useful because but they cannot provide the overridle electrical and the battery safety limits. Okay, so if I talk about a local EMS, if I talk about this local EMS, it should continue essential load management even when connectivity fails. And like the cloud optimization may improve economics, but like the local protection and power limits must remain autonomous. And this CSMS manages basically what the charger identity, firmware configuration, and some meter values, alarms, and like the remote operation as well. Okay, so it is not the same as the EMS, although like one platform may implement both the functions here. Okay, and if I say like this about this aggregator, so this requires forecasting, baseline methods, dispatch logic, and some settlement rules as well for flexible charging. Okay, and for the stationary storage BESS, Basically, it can absorb solar surplus or reduce the transformer peaks, and it also supports in fast chargers and provides backup for selected loads. But here each service consumes battery through output and must be like economically scheduled. Okay, so the reason behind this stationary, it is just for to reduce the transformer peaks, and it helps in support fast charging and provide the backup. Okay, and if I talk about the optimization problem, it normally includes like hard constraints such as like feeder limit, charging limit, battery current, and departure SOC. All these things comes inside this. Okay, so this is basically the EV charging ecosystem or some stakeholder map which comes inside this our charging system. Okay, so different locations create some different devel times power requirements and business models. Now let's classify those charging location. Okay, now as you can see here, there are some types of charging location is shown here. The private charging, community charging, workplace charging, public charging, captive and fleet charging. Okay, so if I talk about this private charging, so this private charging prioritize convenience, right? And electrical safety and low installation cost as well. And if I talk about load management may be required when multiple homes share this one feeder. Okay. Can anyone explain me or tell me about the community charger? If anyone know, you can unmute yourself or you can just speak up. Community charger, where it is located, and how many how we can get the benefit from this. Anyone? And why we have a need of this community charger? Anyone want to say? You can just unmute yourself. And you can also tell me the difference between the private charging and the community charging. Okay, no issues. So basically, this community charging requires what it requires
Hello.
basically. Yes, yes.
It is in the housing society or parking. That is the difference between private and community. But here, people understanding is very important.
Okay. So yeah, that these things are like already mentioned here. So yeah. So basically, this community charging location, what it tells basically here, the charging requires access control, right? And a fair location or some parking rules will be also there, right? And it often shared billing or some resident management as well. So this type of community charging is located at housing society where there is some shared parking as well. But we cannot use this type of charging because this charger will also cost higher than the private charging, because in private charging we can easily mount our charger at our homes. Okay, we can just charge our vehicle one time, then the other vehicle will charge until it gets charged, right? And if I talk about this workplace charging, so its benefits we get that from a long dwell time and some solar coincidence, but it also needs some employee policy as well. Okay, so these basically workplace charger are placed at factories, office, educational institutions, hospital, corporate parking. All these comes inside this. Okay, if a visitor want to access this workplace charging, so he needs some access or he needs some card to park his vehicle or charge his vehicle. Okay, and there is also like there are some also if I site load conditions as well here. And if I talk about public charging, so this public charging requires high availability, right? And accessible payment as well, or some lighting support, we also here need, then the maintenance as well. So these public charging stations are usually placed at these locations. Okay, and last one we have the captive and the fleet charging. So basically this fleet charging is optimized around route energy, okay, or the vehicle availability. Like you can see here the taxi fleet, delivery fleet, bus depot. Okay, so they also demand charges, and sometimes like opportunity charging during the route as well. Okay, so this is basically the types of charging location. I hope you will remember all these charging stations. Okay, now let's move forward. Okay, so here you can see that the electrical energy, power, and the charging time. Okay, so we know that the battery capacity in kilowatt hours tells us how much electrical energy the battery can store or deliver under defined conditions. And power in kilowatt tells us the rate at which energy is transferred, right? And times connects them if power were constant and losses were ignored, right? So energy equals power and multiplies by time here. So if we see that we have a 30 kilowatt required, okay, 30 here, 30 kilowatt hour is required, which is divided by 6 kilowatt. The average we got here is 5 hours. So the stress for this is basically the stress board. Uh, like a charger may be rated at a 7.2 kilowatt, as it is mentioned here the 6 kilowatt. So the charger may be rated as 7.2 kilowatt, but it delivers less because of the supply voltage or some vehicle limits or thermal derating is also the reason. So a DC charger may peak at 150 kilowatt, but average for less over a 10 to 80% session, because the power curve changes in this supply. Okay, so if I talk about the correlation, it is P equal to V into I for the DC, for DC, and E equal to P into T, when power is constant here. Okay, and charging time is like a integral of dE by dt. Sorry, dE by P. Okay, so which is why an average power estimate is used in practical calculations. And for a three-phase AC, we know that we need a three-phase AC. So active power is approximately will be like P equal to SQRT 3 into V and L into I into power factor we will put here. Then we can include the efficiency as well. So the vehicle onboard charger and supply determines the usable current. Okay, and like energy required between the two SOC values, that is like state of charge values, can be estimated as usable battery capacity and change in SOC. Okay. And for if I say about a 60 kilowatt hour unusable pack from if you want from 20 to 80%, the battery energy increases in about 36 kilowatt. That is the reason behind this, that the grid energy can be estimated. If I say like this grid energy, which can be estimated by dividing battery energy by overall charging efficiency. Okay, so at 90% efficiency, adding it will add around 36 kilowatt hour to so that the battery may require up to 40 kilowatt from the grid. Okay, and the peak power, if I would say, the peak power affects marketing or a short intervals average power determines sessions. So and like the infrastructure utilization is also there. Okay, so this is basically about the electrical energy, power, and charging time. Just give me a second, guys. All right. Now let's move forward and understand what factors affecting the charging time. Okay. So around it, this actual charging power, around this you can see all the factors that push the needle up or down. Okay, initial SOC, target SOC, which basically defines how much energy is needed, and the battery capacity here determines the size of that energy requirement, and the vehicle AC or DC limit, which caps what it can accept, or while the charger rating caps what the station can supply. Okay. So a cold, if I talk about a cold battery, so a cold battery like may restrict charging to avoid lithium plating, or like a hot battery may reduce current to control the temperature. And basically, high SOC, this high SOC usually causes tapering because cell voltage approaches the upper limit, and cable and connector temperature can like trigger the derating. Or if I talk about a shared station may divide power among vehicles, or like a EMS may reduce charging to remain below a transformer or demand limit. Okay, so if I say like a useful engineering model, how we can say that it is basically the P actual, power actual, sorry, just that is power actual equal to minimum power EVSC. Here we can include power vehicle, power of battery, power of cable, power of site, power of shared, power of thermal. All things will come inside this. Okay, so this is how basically a engineering model looks like. So how you can calculate the basic factors? You can add all these things. We have first what we have taken first, that is the P actual. So we have included all these, the PV, ESC, battery, cable, power side. So each term may vary with the time. Okay, and the battery power will and the battery power limit is derived from basically allowed cell current or and battery voltage, or while also like considering the cell imbalance, SOH, internal resistance, and some fault status as well. Okay, so these are basically the factors which affects. Okay, and one more thing, the auxiliary loads like such as battery heating, cable conditioning and coolant pumps. I mean, like not all grid power becomes, which is not all these grid powers become stored battery energy. So, but it affects it. Okay, so this is the factors which affects our charging time. Okay, and you can see here the charging power curve across state of charge. Okay, so this is basically this horizontal axis is the battery state of charge from 0 to 100%. Okay, and this vertical left axis you can see here is the charging power, which is up to 160 kilowatt. Okay, and the right vertical line you can see here the battery temperature here from 0 to 80 degrees Celsius. And one more, that the right axis you can see here is the battery temperature degree Celsius. So and one more you can see here the blue line, this one blue line, it's showing it is showing the power, and the red curve is showing us the temperature. Okay, so in the initial conditioning region, the vehicle verifies safety and battery condition from 0 to 20%. So this is what exactly it is showing. And from 20% to 80%, you can see here it is the high power region, right? And here will be there will be high charging current, and rapid SOC will increase here. Okay, and in this region it is limited by charging charger, battery, and temperature. Okay, so from 20 degrees, around 20 to 23 degrees, 23%, from 23% to 80%, it is showing us the limited power, right? As you for example, if you have seen, whenever you charge your mobile phone, from the 0 to 20%, it gets charged very fastly, but after reaching a certain percentage, it will get slow down, right? And then you will see it will like charge your mobile phone up to, suppose your mobile gets charged in 1 hour, and suppose up to 80%, it can takes up to around 40 minutes, but from 80 to 100%, it needs around 20 minutes more. So here basically that this is same happens here. The taper region showing that the charging current gradually decreases, right? And cell voltage here approaches the upper limit, and the charging power falls at high SOC. So it is showing us the same thing, that how the power tells us the state of charge thing. Okay, and here you can see that the battery temperature also will comes degraded here, and it reaches up to 30, and here is a little bit increase, you can see here at the center part, from 23% to around 80%. Okay, so this is just for the curve you want I want to show you. Okay, so and this is blue, just the moderate power we are getting here. Okay, and whenever your vehicle gets charged at the end, or a fully charged, so it will stop charging, as the BMS protects it, and it just stops the charging part. Okay, so this is also like BMS also helping us to continuous monitor the current SOH, so, or the temperature, and in the background it is also doing the cell balancing as well, right? And can anyone explain me about cell balancing, how cell balancing works? If anyone know, you can just unmute yourself. How cell balancing works, anyone know? Anyone?
It
I
may
think you are
be,
from the electrical background. Yeah,
it
what's
may
your
be
name first?
Suryavanshi, sir. Satish Suryavanshi.
Okay,
Hello.
Suryavansh, yes, go ahead.
Cell balancing means it may be avoiding the overcharging. The BMS system will control or it will cut off the charging if the temperature goes high.
Okay, so
Thereby, it will
yeah, could you tell me about how many types of cell balancing is used,
no.
by BM?
Basically, I am from mechanical background, so
Okay,
in
okay.
theory, I have not learned about this in electrical
Okay,
engineering.
okay, Suryavanshi, no issues. You said very great. No issues. Okay, so basically cell balancing, there are two types of cell balancing. Anyone want to say? You can just unmute yourself. I want you to speak up.
Yes, sir. One is active balancing and the second one is passive balancing.
Okay. So how active balancing works and how passive balancing work? Can you just explain me?
Yes, sir. In my understanding, I think passive balancing, actually, we are wasting some kind of energy by using resistors kind of things. So all the cells are identical, right? So if one cell in the battery pack gets charging in very fast manner, means the BMS will do the things. Yeah.
Okay.
And the
Yes, great.
active balancing
What's
means
your
we
name?
have to transfer that extra additional energy from that fast charging cell to the lowest charging cell. That is active balancing.
Yes, exactly. So this is how basically the active and passive balancing works. So passive balancing, how it transfers the energy, it transfers in the form of heat or to the resistors. Okay. So, but in the active balancing, it transfers the energy from a high energized cell to the lower energized cell, so it balances all the cells. Or suppose your vehicle is when your vehicle is running in a running condition, the battery will degrade or like all the cells will degraded equally. So that is the how basically the SOC and state of charge or cell balancing works. Okay, now let's move forward. So now let's understand about the BMS role in determining allowable charging power. Okay, so it like this BMS like continuously monitors individual cell voltages, pack current, temperature, and like it also estimates SOC, SOH, and internal resistance as well. Okay, but BMS like doesn't simply say charge or do not charge. It what it does, it calculates an allowable current or power that can change many times during a session. So if the coldest cell is too cold, or like the hottest cell is too hot, so the highest cell voltage is near the upper limit, or the pack has aged and like resistance has increased, or like the BMS lowers the allowable value. Okay, so one more thing comes is that stress the cell level principle. Okay, so what it explains, like it tells us that the pack is limited by its weakest or most constrained cell, not only by average pack voltage. Okay, if one cells can tell the cell can force current reduction, so one cold region can create plating risk as well. Okay, so the charger follows the permitted limits communicated by the vehicles, while independent protection remains ready to open contractors if a serious fault occurs. Okay, so one more thing, like the internal resistance causes also the heat generation and voltage risk also under the charge as well. Okay, and how aging increase? Aging can increases the resistance or reduce the save power even if like capacity remain unusable, right? So this is basically how the BMS and the BMS role in determining the allowable charging power. Okay, now let's move forward. Understand about this AC charging principle. So the AC EVSC basically provides controlled and protected AC connections. Okay, it detects the vehicle, verifies protective earth continuity, communicates an available current limit, and also what it works, it closes the contactor only when the conditions are safe, or like monitors leakage and record the session as well. So but the important conversion occurs inside the vehicle, that is the onboard charger, which converts grid AC into controlled AC. Okay, and it is also suitable for the high voltage batteries, and it normally includes rectification, power factor, this power factor corrections, isolation when it requires. Okay, and some like high frequency conversion as well. Okay, so basically this the if I talk about this power electronic system, these are carried in the vehicle so that the like external EVSE is simpler, but it is and also it is less costly. So this there is some like sometimes the onboard charger is limited by vehicle cost as well and the size. Okay, but the main thing is that the this OBC basically regulates battery current according to the BMS request. Okay, and it must meet the EMSC insulation, thermal, or efficiency requirements, across a wide input and battery voltage range as well. Okay, and here one more thing happens is one more things matters is like the power factor correction. Basically what power factor corrections uh, does, it just reduce the reactive current and harmonics which is drawn from the grid, and it this power factor also uh, um, like improve the utilization of the electrical supply as well. Okay, so all these things comes inside this, and this is how basically the charging principle works, and it is supplied directly to the vehicle high voltage battery system. Okay. So now you have seen like there are two types of AC charging available, AC charger and DC charger. Okay. So how AC charger and DC charger works, as it is as the characteristics are already mentioned here, that AC to DC conversion occurs inside the vehicle as the vehicle uses vehicle onboard charger and normally lowers or medium powers. Okay, and we have also like lower installation complexity in this, and it is basically common at home, offices, destination locations. And on the other hand, if we talk about this DC charging, here AC to DC conversion occurs inside this charging station, and inside this charging station the components are placed like RCCB, MCB, RFID card, some capacitors, resistors, transformers. So all these types of components are placed inside this DC fast charger. So it helps the conversion. It helps in conversion from AC to DC. Okay, so you don't have need here the of the onboard charger. You can directly charge your vehicle with the help of direct DC supply and supply it into your battery pack. Okay, so normally used for it is fast charging, and it is mostly you can see see in the highways, or some, suppose if you see any restaurant near highway, they also place this DC fast charger in their locations, because if a person is traveling from so far, or suppose so there maybe he has an electric vehicle, so he want to take eat some food, or want to charge his vehicle as well. So like hotels or restaurant also provide like right now are providing this charging station. Okay, okay, just give me a second. Okay, all right. So as we know that heat generation, or the G, we can see here by I square R. What I square R is? Loss. Basically what is showing, the power loss, current, and the resistance. Okay, so the current is basically squared, so a modest increase in current creates a much larger increase in resistive heating. Okay, and this heat appears in where? Cells, bush bars, contactors, cable conductors, and power electronics components. Okay, so if one more like example is given here, is that the equal power comparison from 400 volt system to 800 volt system. Okay, so at like 200 kilowatt and an ideal 400 volt system needs about 500, around 500 ampere, while like an a system which is 800 volt needs about 250 ampere. So if resistance were the same, so halving current reduce resistive loss to 1/4, and if I say like in reality, resistance and component design also change, but the basic advantage remains higher. Basic advantage remains higher voltage, and it can deliver the same power at lower current. So battery cells still generate heat, or like semiconductor switching and some conduction losses will remain, and like a high voltage increases insulation or something like a rating requirement, so the system uses liquid cooling there, or a refrigerant assistant cooling as well. Okay, so there the battery preconditioning and the conductor temperature monitoring helps to keep the operation within the safe limits. Okay, so this there are some channels inside the battery pack through which the liquid cooling flows and helps the battery to remain into the safe limits. Okay, so cell, if I say if I would say like the cell, basically the cell heat includes irreversible like losses and some electrochemical heat as well. Like at high charge range, the temperature gradients between cells can become as important as average temperature. Okay, and if I would say like contact resistance, the contact resistance can increase due to wear or contamination or poor matting, or like if there is a local connector. This local connector, what it does basically, it just this local conductor temperature sense or helps detect the hot spots before the damage. Okay, so the thermal management capacity is just finite. Only the coolant or the refrigerant reaches its limit. Okay, so the BMS must, that time what it do, it will reduce the power. Okay, so the main thing behind this is the coolant and the refrigeration, because they always reach its level. So we, the BMS helps that time, or it just reduce the power. Okay, so high charging basically power requirements across, there are some requirements shown across the vehicle segments. So they consume these vehicles depending on the how much power they consume, as it is mentioned at 50 to 3 kilowatt hour, sorry 3 kilowatt in the, if we say that the electric bus uses around 150 to 600 kilowatt, and if I would say heavy vehicles, it is a megawatt, 1 megawatt. So 1 megawatt charging system, here we have MCS for heavy duty time critical charger charging. So like they are like a city bus like with like overnight depot charging may use moderate power, while a bus at an end of route pantograph station may use very high power. Or if I would say like a passenger car which is used as a taxi may need more frequent DC charging than a private car. Okay, so the charging basically the charging cabinets often contain repeated power modules. So the control system can combine modules for one vehicle or share them among dispensers. So the modularity improves serviceability and like allows a site to scale, but the upstream transformers and feeders must still support the total coincident demand. Suppose if I would say like the like required average power can be estimated by energy needed, right, and divided by available dwell time. Okay, and if I would say that the peak energy, so that the peak capability must then be checked against the vehicle charging curve. And suppose if this heavy vehicle, this heavy duty design challenges include very high current, liquid cooling cables, and connector handling, transformers capacity. So it, here in this, basically the grid demands its peaks. Okay, and like if I would say a megawatt class, this basically megawatt class labels does not like amplify continuous operation at maximum, or like vehicle voltage or thermal limits. It just shapes the actual basically session. But basically these are just the different power modules shown here. Okay, the grid connection and the modular power sharing, we are getting here the total MCS. Okay, and here are some different applications of where the we need power charging power requirements. Then we have conductive charging mode is charging mode here. Okay, so basically the mode here just describing how the vehicle is connected to the supply and where control and protections are located. So here basically these connectors describing basically what the physical interface. So this distinction like prevents many classification errors as well. So if I say about this mode 1, it uses a standard socket with limited dedicated control, okay, and is basically generally unsuitable or like restricted for modern public EV charging because protection and communication are minimal here, okay. And if you can talk, if I would say about this mode 2, so in this mode 2, it just adds in cable control and protection devices, and it is commonly used for portable or emergency charging. And then we have the mode 3, it is a dedicated AC EVSE charger, so with the control pilot communication and like a control contactor operation. And then we have the mode 4, which is DC charging, so it is a dedicated DC charging with off-board power conversion and high level communication, okay. And if I talk about the stress part here, that the national regulation and product approvals determine what is permitted. So it just showing you all these things, that some limited protection and all these things, okay. But if usually this mode to basically control cable controls and protection devices can monitor protective conductor and control energization, but the upstream socket and wiring must still be suitable for the sustainable load. And this mode 3 just supports the dedicated AC charging with current capability and like a controlled energization, okay. So these are the basically conductive charging modes. I hope you will remember this, and if you want to make some notes, little notes, you can just write it down, the mode 1, mode 2, what it does, okay. Now let's understand about this charging standards. So basically, as you can first see here, that the first we there are total 4 layers here: the connector layer, vehicle communication layer, charger backend layer, then we have the network roaming layer. Okay, so at the connector layer, we have IEC 62196. So basically, it is defining family of plugs. What is defining? It is just defining the family of plugs, socket outlets, vehicle connectors, and inlets. And at the conductive charging system layer, this IEC, uh, basically this IEC 6185 just addressing system requirements and charging modes. So at like a high level, at the high level communication layer, we use ISO 15118. It supports functions such as plug and charge, charging negotiation, and directional communication. And below the vehicle and charge, we use OCCP. So basically, it just connects a charging station with a charging station management system. How it is communicating, or how it is the communication is happening, that this OCP connects a charging station with a charging station management system. Okay, so it just connects the organization or networks for roaming, location, traffic tokens, okay, or like a charge detail records. So these protocols solve different problems, and using one does not like replace the others. But in the India specific box, if I would say like that BIS, this standard, or the CEA. So basically, this BIS adopts and publish relevant Indian standards, while CEA is and Ministry of Power requirements addresses safety and infrastructure development. So for a real project, the exact part and current edition of the IS 17, this if I was IS 1701 series, or like for a CA safety provision and ministry guidelines must be checked before this. Okay. So this is about the charging standards overview, and if you can remember this, or you can just check the screenshot of all this. Okay. Now let's move forward. Let's understand about the main charging connector families. Okay. So a common AC connectors basically includes type 1 and type 2. While the DC or the combined families uses CCS combo 1, CCS combo 2, and we have SHADMO, GBT, SAE, this J3400, Xiaoji, and we have a megawatt system, megawatt charging system. And if I talk about the light vehicle, that uh, uh, light EV and the socket. Like it based on solution and like add further regular variation there. So let's first understand what CCS tells us. Basically, this CCS just are like a common reference point for many passenger vehicle installation, while this SHADMO and GBT may remain at some sites or some vehicle categories. But the legacy of Bharat, this Bharat AC and DC, this is the legacy installation. Uh, Basically, in this, the just actually my laptop got discharged. Just a second. I will connect my charger. Just give me a minute. All right. So where we were? Yeah. So the legacy of this Bharat AC/DC interface are like proprietary 2 and 3 wheeler connectors, which required carefully vehicle specific variations. Okay, so the Bharat stage is also Bharat stage AC or the Bharat DC legacy installation is all over the India right now. And these types of other CCS chargers are and the different types of categories. These are the some connector families of these. Okay, and about this connector rating, I would say basically it does not guarantee charger or like the vehicle power. So the complete path is limited by the lowest component rating. Okay, and if I talk about this megawatt charging system, so it is intended for heavy duty or here in this basically megawatt applications, and it requires specialized handling as well. Okay, or cooling and like site safety infrastructure as well. So these are the basically connector families, and this maybe these are the type 1, type 2, and combined charging system. So basically it is commonly associated, this type 1 is commonly associated with single phase AC charging, and as a historical use in North America, and Japan has also used this. Okay, and the type 2 which supports single phase AC or the 3 phase AC charging as well, and it is usually widely used in European and many Indian charging application also use this type 2. Okay, then we have the CCS combo 1, combined charging station combo 1. We have we combine the type 1 style AC section with additional DC connection. Okay, then we have the CCS2, same. So basically in this I would say like this type 2 can like doesn't guarantee a particular DC peak voltage, but it is commonly used for DC charging in India as well. Okay, and we have one standardization is as well, which covers standardized, or we have a configuration as well here, which covers DC and combined AC vehicle couplers. And if I would say about this SHADMO GPT, and it is the dedicated DC charger system. And it has a V2C communication, vehicle to vehicle communication, vehicle to charging communication, and it is used on several earlier Japanese EV model. Okay, so it is Japanese EVs uses this type of charger, SHADMO charger. Then we have the GPT. It is basically in the majorly used in the Chinese vehicle. Okay, so Chinese charging interface family comes inside this GPT charger, and we have a separate AC and DC arrangement. So these are basically for the DC, and these are for the AC arrangements. Okay, and it is used in light and commercial EV applications. And I would say about SAE. This is a standardized North American EV coupler, or like a practical electrical and safety requirements we have required, and it is primarily for the North American application. So it is also used there. And megawatt charger, it is just we have just discussed about this, that it is majorly used in heavy commercial vehicles, trucks, etc. Okay, so this is about the SHADMO. Then we have a charging communication layers. So let's understand about this charging communication layers. And I hope if you have attended about the CAN webinar that I had conducted, so in that I had also discussed about some 7 layers OSI model. In that, the only layer 1 and layer 2 works with the CAN system. So similar types of thing is also here, that there are 5 layers. Okay, so at first layer, what it tells us the physical connection. Okay, what it is telling, it is telling us the physical connection. So the question is physical, that is the connector inserted, or is the is like protection earth is present, and is the connector is locked or not. And if I would say at layer 2 we have a basic control communication. Okay, so in the layer 2, where what we have, it is a basic control signaling, which establish connection state, or like this available current, weathering energization is also like permitted here. And in the layer 3 we have a high level vehicle communication. So this layer 3 adds high level communication between EV and the charger. So here the system can exchange vehicle identity, like the battery voltage, or requested current, state of charge, and some advanced function as well. Then in the layer 4, there we have a charger to be backend communication. So basically, layer 4 moves outside the local charging interface. Okay, so the station communicates with its backend for authorization, transactions, or configurations, firmware management. Okay, then in the layer 5 we have a network and roaming communication. So this layer 5 connects service providers or charging network for location, tariff, or some session or billing exchange, all these things. Okay. So these are how basically there are 5 layers behind this communication, how the vehicle communicates with the EVSE charger. Okay, first we have physical connection, then the basic control communication, we have a high level vehicle communication, then charger to backend communication, then at the end we have a layer 5, we have a network and roaming communication. Okay, so physical and basic control layer should fail it should fail safe, and remain independent of cloud services. And if I was say like the about the cyber security requirements, that the charging cybersecurity requires may increase up the stack or device identity. Okay, so we need there the certificate management, authorization, etc. All these things. Okay, so these are basically the communication layers through which the vehicle communicates with the EV charger, EVSC controller. Okay, and telling us the exact uh, state of charge or how much time it will take to fully charge our vehicle. Okay, so this is the basically the similar thing that the vehicle communicating with the EVSC using the vehicle charger interface. Same thing I just discussed with you. Okay, so basically it is just the same thing. Now let's move further. So here is basically telling about us the standardization, which is 15118, and plug and charge, high level communication. Okay, so here basically it is a family of standard. We just discussed some standards as well before in the last slides. Okay, so for high level communication between the EV communication controller and the charging station communication controller, it's like its capabilities can include vehicle identification, charging limits, okay, suitable exchange, some secure communication, smart charging, and bidirectional function as well. Okay. Okay, so this ISO certification, ISO standardization is widely associated with the first generation plug and charge implementation, while I would say ISO 1118 basically this is just expand and like modernize the function, including bidirectional power transfer. And in this we have like some certification as well, so which basically digital certificate just supports like the compatibility and authentication. Okay, so this was about that, and this is the same thing. It is the process shown here, as I know. Sorry, as I think that you already know about this. That how do you have to park the vehicle, then you have to plug in. This is basically how the process looks, and the vehicle authenticated automatically that the charger is fixed or locked. Okay, and how much time it will take, or the how much power like is it with the that the charger you have used is the OBC or you have directly plug in the high voltage DC power. So then in the charger there is one meter is placed inside it. It will continuously monitor the units that it has your vehicle has consumed, and at the end whatever the billing will come. So by reading the units, suppose there are like 100 units of energy is used. Okay, so then you have to pay for that 100 units, then you can just drive. Okay, one charge point protocol is mentioned here. Okay, so basically here it is also showing that the authentication part. Okay, sorry, the protocol that charging stations and like management system, it just like allows a charger from one vendor to communicate with backend from another vendor. Okay, which is provided both implement capabilities or like profiles and have been like properly integrated and tested. Okay, so you can use this process. So road basically just that here the transaction starts. Okay, you can see here the boot authorized, then the start we have the meter value, then it will stop. So this is what it showing that the charging station management system. It just it should like this what I would say, like this charging station management system should not assume like every charger, but it supports every optional function. Okay, and the capability of this CSMS is that it discover and provide a documented feature which is basically important for the profile. Okay, and the smart charger part, I would say that basically that these smart charging profiles set some limits over the time, but they remain subordinate to local electrical and vehicle constraints. Okay, so the widely used, you can see here the OCCP. Basically, it's just telling us the message logs which are valuable for diagnose, but it also must be protected because they can contain operational and user linked data. Okay, so this is just telling us that this is basically released in 2025 and adds some certificate standard here. Okay, and some battery swapping also use this type of authorization operation as well. Okay, so suppose you want to you are doing battery swapping, so you must authorize first as well. Okay. So basically this OCPI and OCPI roaming and what exactly this user authentication is. So we know that a charging equipment on network A is operated by one CPU. Oh, sorry. While the customer like may hold an account with a mobility service provider connected to a network B. So OCPI just exchanges the information that lets those organization recognize the user. Okay, and and they shows the charger location and the traffic. Okay, so this like if I would say like these all these data locations, connectors, availability, traffic, tokens, session, all these things, charging details, billing information. So like the user may use or like the user may provide this RFID card. Okay, so this RFID is also placed inside the charging station, or if there is a wall mounted on a charger, so the RFID was also inside this. So they use an app or scan a QR code using a payment terminal, and receive can you can they can receive the remote authorization, or you can just use plug and charge. Okay, so the roaming interface here in this carries the relevant identify and session information between the organization. Okay, so basically it just if I would say that a CPO is just operates the charging infrastructure, okay, and manages the driver contact and the service. Okay, and uh, if I would say like the roaming security, which requires authenticated endpoints or like secure transport identifier governance, so against all this sometimes there will be a fraudulent tokens as well. There will be fleet identification, the remote operator authentication. It also there are some common user authentication methods available here. Okay, so this is basically the charging station hardware architecture is shown here. Okay, so here in this basically the input power section basically here just receives the utility supply and includes in this the isolation metering uh, or breakers, some surge protection as well. So this section basically just this section just protecting uh, or the system or the with the help of earthing system as well. Okay, so it just establish a control supply to the charger. Then the power conversion section, if you see there, you can see here the AC contactor for AC EVSE or the rectifier, and DC link stages, output filter. We all have these things in the inside this. So the control section here runs. If I would say this control section runs. Like the charging runs the charging station state machine or communication, or like the main one more thing is that the payment reader or RFID, okay, through which you can connect with the authenticated organization, or you can just make the payment. Okay, so So if I would say that the about this thermal management system, we have a fan, heat sinks, liquid cooling were used, or some temperature sensors and air filter are just for the cooling purposes, because the components can gets heat up while we are charging. Okay, and at the end we have the safety sections. We have emergency stop, insulation monitoring, interlock door switches, smoke and heat detection. So all these things also comes inside this EV charging station hardware architecture. And this is basically the charging station software architecture. Then just we have said seen the hardware architecture. Now we have the software architecture. Okay, so basically the real time, you can see here the charger hardware. Inside the hardware we have a real time controller, manages power, or like power stages, connector logic, metering, all these things. So if I would say that the communication, in the communication layer we have the Ethernet, Wi-Fi, cellular connectivity, and secure transport to cloud platform. So the cloud host the CSMS or user database and tariffs engine. Okay, and here the user application consumes selected data and sends permitted requests such as connector selection or session stop. Okay, and a mobile app, if I would say that a mobile app should not directly command a contactor. It requests a session action through authenticated service. So the cloud here validates the request first, then the charger validates its current state, and the local controller performs the action only if safety condition is permitted. Okay, so the like real-time power control should be deterministic and isolated from non-critical user interface tasks. Okay, and like the local faults logs and event timestamps helps us to diagnose the issue even when the network is unavailable. Okay, so this is how basically the software structure looks like. And this is about the vehicle high voltage and charging system components. We have high voltage systems in the, we have vehicle to grid compatibility, battery pack by BMS, main positive negative contactor, all these things inside this. And in the charging system, we have a bidirectional or OBC or DC charging interface. And we have a EV charging inlet, all these things, EMI electromagnetic interference filter, power factor connection stages, isolated DC converter, all these things are inside this charging system. And some control system through which we can control or communicate, that is VCU, EV communication controller, CAN communication through which we communicate directly with the charger or the battery, or we have a secured hardware module as well, some telematics and connectivity unit as well in the high voltage and charging system. These all are coming inside the high voltages. Okay, then we have a vehicle charging state machine and some safety layers also mentioned here. I hope you understood till now about the users layers, and here we have basically the AI layer as well. So here basically the user layer provides the target SOC, departure time, reserve SOC, or V2G consistent. And here the AI layer predicts and plans. And the safety layer includes here the BMS protection. Okay. And sorry, BMS limits, BCU logic, contactors, pre-charge thermal. So all these things. Okay, so and these are the same thing, the communication standard, and we have some vehicle charging state machine as well, that the sleep, we have then plug-in wake up communication authentication, then the capability exchange, and at the end we have isolation and unlock. And all the data is the request signals, request signals are directly communicate or getting the and this data is getting stored inside the cloud and the aggregator part. I think these slides again come here that we know that the normal charging sequence right now, okay, how the charging sequence looks like. Okay. Okay, now let's understand about this solar battery storage and energy management integration. Okay, so basically, this solar PV or utility grid and stationary BESS. So they feed basically a smart energy controller that decides how much power each charger receives and whether the BESS chargers like charges or discharges. So the here the controller does not create energy, and it just schedules the available energy within equipment and site limits. Okay, and during like a high solar production, the site can directly charge the EV and use surplus power to charge the BESS. Okay, and suppose during evening time or night time, the BESS can discharge to reduce the grid demand or support fast charging. Okay, so the grid here remains the balancing source when local generation and storage are insufficient. Okay, so like a BESS may have sufficient kilowatt hour to support a short peak, but insufficient kilowatt to support several fast chargers simultaneously, or some vice versa as well. But here the both converter powers and battery energy like capacity must match the intended service. And if I would say about the EMS, basically it should enforce transformers, feeders, and contractual demand limits while repeating the BES SOC. Okay, and if I would say about this, the solar self-consumption, the solar self-consumption just increases when flexible EV charging is shifted into solar hours. Okay, often avoiding they often avoid like storage conversion losses as well. So this is how the charger solars helps us to charge our vehicle sometimes directly, but at the off time as well. Okay. Then we have basically the vehicle to control grid. Then basically in this we have we can define BIG. Basically it flows in this, we can just control the one directional charging. And so basically in this uh, controlled or one directional uh, in this, but the timing and the power are controlled. Okay, so the system in this like can delay the charging or reduce the power, or just share a site limit or prioritize the vehicle while still meeting the target associated departure time. Okay, so as you can see, the required input, the what are the required inputs here? We have the present associate, target associate, the departure time, charging capability, all these things, and we have one smart charging controller optimization. And in this, the charging output, we get the start and the stop time as well, and the charging power. Okay, so if if I would say about the feasible V1G controlled unidirectional charging thing. So its schedule must satisfy energy by departure constraints. Okay, so here the integral of charging power over time and after the losses. So it must deliver the required energy as well. So this is just one-way energy flow grid vehicle. As you can see from the grid to charging station, then we can directly charge. Then the main part comes here, that is our AI based mass charging optimization. Okay, so basically this is a basic strategy, like or we can just optimize it or using some advanced AI. Okay, in this basically we use fixed currents or some equal sharing time of use charging and simple delayed start or like in this basically AI becomes useful when the system must predict uncertain inputs such as like arrivals, departures, some solar generation as well. Okay, and here in this the controller roles also comes. So here in this the controller roles comes like it just forecasts the model and predicts the future conditions and okay, so with the in this basically we I would say that AI does not like decide electrical safety here, but it may recommend 80 kilowatt, but the charger and the BMS still cap power, and model should not should never bypass protection or some grid limits or user reserve. So in many systems, the most important component is not a complex neural network, but a well-formatted constraint optimization problem with reliable data. And this is the same thing. The AI-driven charging optimization cycle is shown here. That the historical charging, it it takes or it checks the historical charging sessions and tells the vehicle SOC and energy request. Then also it checks the arrival and departure behavior, and we can check the charger availability as well in this. And the main AI function we get that the charging demand forecasting, or we can just or we can also like predict the vehicle's availability as well. Okay, so all these things helps comes inside this. Okay, so one more thing, like I want to cover a little bit faster. Okay, that's why I'm speaking a little bit fast. Okay, just pardon me for this. So then we have a vehicle to everything, that is charging modes. Okay, so in this basically uh, we have it basically just tells us that destination of energy, not one universal hardware method. So some vehicles provide a dedicated low power AC outlet for V2 L or V2H or some. You can see here the vehicle to load, vehicle to building, vehicle to everywhere. So this is we can use some vehicle to vehicle as well. So all these things comes. There are different charging modes comes inside this V2X technology. Then we have vehicle to grid, energy path, and a control path. Uh, Vehicle to grid is in this basically the vehicle communicate with the charger reports to the charging backend. Then basically the here the backend coordinates with an aggregator, and just aggregator exchanges the request here. As you can see here, then we have the meter and the protection. Then at the end we have a distribution grid. But if I talk about the vehicle to grid control path, in this we have a digital communication. The aggregator is used and it tells us the exact numbers or tells the exact SOC. Okay. This things also comes inside this vehicle to grid aggregation, which is virtual power plant. Okay. So like an individual EV may connect unpredictability and provide only a small amount of power by combining dozen, hundreds or thousands of vehicles. Okay, so an aggregator can offer a more stable, measurable resource to the grid or renewable plant or some commercial buildings. So a virtual power plant is not only a physical generator here. It is like coordinated digital portfolio of these distributed resources are there. So the aggregator just forecasts the availability and reserves more energy, dispatches set points, and measures the response and settles with the participants. Okay, so this is the, and these are some benefits of vehicle to grid and some battery protection trade-off or as well. The technical challenges are the additional battery cycling, conversion losses, battery temperature control, and the commercial challenges including this battery warranty, revenue sharing, all these things comes inside or challenges the B2G has to face. And these are some technical challenges. And this is just shown by the great benefit. And it is shown that the battery wear or some energy losses. Okay, so it is like on a same level here, and it is basically shown here the bidirectional charging architecture. So from this, we are giving back energy from battery to onboard charger, then the AC, then the this from directly this converter inside vehicle just produces the control AC power and gives bidirectional charging. And we have DC bidirectional charging, and this is basically some selection criteria is shown here. Okay, and this is vehicle level V2G implementation roadmap shown here. First, the phase one is the definition, in which we have a AC or DC V2G architecture. Then the second phase, how you can implement in a roadmap. It is shown here that in the phase two, you can do the battery and converter modeling, some charging profile as well. In this, we can see the mill or seal validation. And after the phase three, there will be some laboratory validation and hill communication test. So there includes charger in interoperability, thermal efficiency testing. Then in the fourth, there will be grid and vehicle pilot. So you will verify all these things, and at the end we will check the ISO standards or the warranty standards. Okay, so this is how the implementation, uh, how you can implement the vehicle to level, vehicle to grid. Okay, so this is something about the safety, and I think you must know about this cyber security as well. Like in this, there is a mutual authentication that I just mentioned you that user pay to the charging station, because the charging station has a RFID card, and the charger just user just paid through the app or directly communicate with the um, authenticated person. Then we have the certificate management here, network segmentation, all these things. Okay, so then we also have the ones say for over the air updates here. So you can update your so some business and deployment is also shown here, and that's it for today session. And thank you so much for joining this webinar. Actually, I just want to cover a little bit faster. I have some one other sessions right now as well, so that's why pardon me for this. So yeah, how many of you are in the class right now? Just let me check. Just wait for a few seconds. Sorry, have you created the बोल दो.
So hello everyone, thank you everyone. So I've posted the Google form in the chat box that is for the attendance. Okay, fill that form for the attendance, and that is compulsory. So I hope you enjoyed the session, and if you're having any question, so you can ask. Sir is open to answer your question. Anyone having any question? And once you will receive the certificate, please do post on LinkedIn using tagging ISI India. And you can also write your review on Google. And let me send your send like in chat and in the chat box what are the topics you want like in the next session. So we'll see the trainers, and accordingly we can plan the next session in next week. So you can suggest you, and you can give some suggestion for the next topic. And if anyone having any question, you can ask. Okay, so thank you everyone. So you can fill the form and you can leave the meeting, and we'll connect for the next session. And you can give me a suggestion like in the chat box for the next topic. Once you will send your suggestion, we'll prepare the next topic. So thank you everyone.